this lecture we continue the discussion on the all integer dual algorithm. So, we use the same example that we saw in the earlier lecture to explain the algorithm further. So, this is the example that we will be looking at. It is a minimization problem with all constraints greater than or equal to. As I mentioned in the earlier lecture, this example is different from the previous example that I have used to explain the all integer dual algorithm. We will proceed by taking this as an example. So, we first set up the initial simplex table. We add 3 surplus variables x4, x5 and x6, which become the basic variables to begin with. So, we begin with x4, x5, x6. The 3 decision variables x1, x2 and x3 are the current non-basic variables. So, we write them as minus x1, minus x2 and minus x3. Now, it is a minimization problem and it is a dual algorithm. So, dual is feasible, primal is infeasible. So, this is written as maximize minus 8x1, minus 4x2, minus 6x3, which would give 8, 4 and 6 here in the z values. Now, we write this as x4 equal to something. So, there will be a minus x4 here. So, equal to 18. So, x4 goes to the other side, 18 comes to this side. So, we get minus 18, minus 4, minus 3, minus 6. Similarly, minus 15, minus 2, minus 3, minus 5 and minus 20 with minus 9, minus 6 and minus 3. So, we have set the first simplex initial simplex table and we now have to define the all integer dual cut. We saw in the previous lecture that the dual cut has to satisfy certain properties. First of all, it has to satisfy the fundamental cut equation that we saw in the previous lecture. So, we will now define or compute a h and substitute that h into the fundamental cut, so that the fundamental cut equation or inequality is satisfied. Now, we wish a few things to happen. One is that we want to maintain the all integer nature of this table. So, if we wish to maintain an all integer nature of this table, then a pivot, we have to have a cut in such a manner that the pivot element has to be plus 1 or minus 1. The reason is, in the next iteration we are going to divide every element of the pivot row by the pivot element and every column, every element of the pivot column by the negative of the pivot element. So, that is the only place where we divide. In all other places it is multiplication, addition and subtraction. So, if the original table has integers, the integer property of the table will be maintained. Now, we have to ensure that the division does not create fractions, and if the pivot is a plus 1 or a minus 1, then the all integer nature of this table will be retained. So, we wish to have a cut such that the pivot element is plus 1 or minus 1. Now, in an all integer dual algorithm, if we assume that this is going to be the pivot column, so there will be a minus 1 here, and in the next iteration the corresponding column will be divided by the negative of the pivot. So, if we have a plus 1 here, then the corresponding element in the next iteration will become minus, and if we have a minus 1 here, it will be plus. Since we want to maintain the dual feasibility, we now have to have a pivot which is minus 1 and not plus 1. So, all integer dual algorithm will always have pivot equal to minus 1. So, pivot equal to minus 1 will ensure a couple of things. Number 1, pivot will, the minus 1 will retain the integer character of this table. Number 2, it will also retain the dual feasibility of the corresponding column in the next iteration. And since every element of the pivot row is divided by the pivot, if there is a negative here, then that negative will become positive because you are dividing by minus 1, and therefore, one of the currently infeasible variables will also become feasible. So, for all these reasons, it is good to have pivot equal to minus 1 in an all integer dual algorithm. but then we also have to find out a H which satisfies the fundamental cut and results in a pivot which is equal to minus 1. So, in the previous lecture we were looking at some possible values of H. So, we first started by saying H equal to 1 by 9, if we do H is equal to 1 by 9, H is equal to 1 by 9 can definitely give us a pivot of minus 1. So, let us try H is equal to 1 by 9 and apply that H equal to 1 by 9 to the fundamental cut equation. So, when we have H is equal to 1 by 9, our cut will become a slack variable S1 will be introduced. So, minus 20 by 9 lower integer value will be minus 3, minus 1, minus 1 and minus 1, because 9 into 1 by 9 lower integer value there is a minus sign. So, this becomes minus 1, 6 by 9 is minus 1, 3 by 9 is also minus 1. So, we can actually pivot on any one of these. Now, let us also try to understand which one out of these we can pivot. Actually, we have minus 1 here, minus 1 as well as minus 1. So, we could pivot on any one of these. So, in some sense any one of them can be an entering column. So, let us first see whether what happens if we pivot on this, and then understand why we should not do that and why we should pivot only on this 4. So, first let us try and check what happens when we pivot on this 8. So, when we pivot on this 8, the next iteration x1 will come here. So, x4, x5, x6 and x1. So, I will have minus s1, minus x2 and minus x3. So, I am going to assume that this is my pivot element. So, what will happen is I divide the pivot element becomes 1 by pivot element. So, minus 1 will become minus 1 here. Divide every element of the pivot row by the pivot. So, this becomes 3, this becomes 1, this becomes 1. Divide every element of the pivot column by the negative of the pivot. So, it will be retained as 8, minus 4, minus 2 and minus 9. So, this one will become, this is 0 at the moment. So, 0 minus 8 into 3 will give me minus 24 and I can fill this column. But more importantly I am going to come here. So, this element will become 4 minus 8 into 1 will give me minus 4. Similarly, 6 minus 8 into 1 will give me minus 2. So, when I pivot on this 8 and when all of them have a minus 1, it is not advantageous for me to pivot on a larger number here, even though I could have chosen any one of them to be the pivot element. So, automatically this makes us understand that amongst the minus 1 elements we have to choose that column which has the smallest value here, so that we get the dual feasibility maintained. So, let me just show that also. So, let us try and pivot on this. So, this becomes the pivot. So, x2 enters the solution. So, x1 remains here. And S1 comes here. So, now once again this will become minus 1, 3 plus 1 plus 1, divide by the negative of the pivot. So, you get 4 minus 3 minus 3 minus 6. Now, this will become 0 minus 4 into 3 minus 12, and we can fill this. Now, this will become 8 minus 4 into 1 4, and this will become 6 minus 4 into 1 2. So, when I pivot on this, I realize that the dual feasibility of this row is maintained. So, I have to do two things, one is the pivot element has to be minus 1, and second is if I have more than one minus 1 element there, then I have to ensure that the entering column is the one that has the smallest value of this. So, that is the second learning that we get. So, we can actually use h is equal to 1 by 9 to get this all integer dual cut, and then we can pivot on this or make x2 as an entering variable and then we proceed. So, it is perfectly allowed, and this is obtained by substituting h is equal to 1 by 9 in the fundamental cut equation. We have already seen in the previous lecture that this comes, because h is equal to 1 by 9, the lower integer value of h will be 0. So, this term will go, so only this will be there. Similarly, this term also will go. Now, what we have essentially done is to multiply with 1 by 9 and take the lower integer value, which is what is shown here as well as shown here. So, for h equal to 1 by 9 we can write it. So, we could proceed with h is equal to 1 by 9, but then we go back and see in the previous lectures as well as in the last lecture that I have used a slightly different way to compute h, and when we actually computed the h, we ended up having h is equal to 1 by 6 and not h is equal to 1 by 9. Right. So, let us now see, this is one possibility that I can use h equal to 1 by 9 and I can proceed. Now, let me look at some other ways of doing this. Now, let me go back to this equation and see the other one. After all, we chose h equal to 1 by 9 by choosing the largest of these numbers and saying when I have h equal to 1 by 9, I will definitely get a minus 1 here, a minus 1 here and a minus 1 here. Now, what happens when I get h is equal to 1 by 3? Suppose I use h is equal to 1 by 3, I would still get a minus 1 here, but I will get some other numbers here. So, when I get h is equal to, let me try h is equal to, so I now say h equal to 1 by 9 is okay, I am able to get that. This is acceptable because it is able to maintain the dual feasibility, it is able to do everything that I want to do. The only difference is it gave me from 0 it moved to 12, alright, the solution moved to 12 because lower integer value of 20 by 9 is, in this case it is minus 3. So, 4 into 3, 12 is the gain. Now, if I try h is equal to 1 by 3, my cut will look like this. I have S1 here. So, 1 by 3 will give me minus 7 because 20 by 3 lower integer value is minus 7. This will give me minus 3, this will give me minus 2, this will give me minus 1. And I know that I have to pivot only on the minus 1. Therefore, this automatically forces me to have this as the entering column. We already know that this is not a very comfortable situation, but let us see what happens. So, when I do this again, I realize that I have minus x1, minus x2, minus s1, x3 enters the solution, x4, x5, x6, x3. So, this is my pivot element. So, pivot becomes 1 by pivot, so I get a minus 1. So, this becomes 7, this becomes 3, this becomes 2. This is divided by the negative of the pivot. So, the same column remains 6, minus 6, minus 5 and minus 3. Now, this value will be 0 minus 6 into 7 minus 42 and I can fill the rest of them. This value will become 8 minus 6 into 3, 18, which is minus 10, and this value will become 4 minus 6 into 2, which is minus 8. So, pivoting on h equal to 1 by 3, which if we look at this, we pivoted on 1 by 9 and said it is acceptable, but pivoting on 1 by 3 is not acceptable because we lose the dual feasibility of this, which we do not want. It is a dual algorithm, we want to maintain the dual feasibility of this. So, we will not pivot on 1 by 3 here. The third and the last alternative is to try and pivot on 1 by 6. So, try and pivot on 1 by 6. So, if we pivot on 1 by 6, the constraint or the cut will become 20 by 6 is minus 4, 9 by 6 is minus 2, minus 1, minus 1. So, 9 by 6 lower integer value is minus 2, 6 by 6 is minus 1, 3 by 6 is minus 1. We already know that between the two minus 1s or amongst the several minus 1s if we have to choose the entering column as the one that has the smallest value. So, we could do this, x2 enters the solution, and when we do this we also realize that so you have minus x1 minus s1 minus x3, you have x4, x5, x6 and x2. So, this is our pivot. So, once again pivot becomes 1 by pivot, so minus 1, divide by the pivot element 4, 2, 1, divide by negative of the pivot, so 4, minus 3, minus 3, minus 6. So, this will become 0 minus 4 into 4 minus 16, and I can fill the rest of this. This will become 8 minus 4 into 2 0, 8 minus 4 into 2 0, 6 minus 4 into 1 2. So, at h is equal to 1 by 6 I can proceed just as I can proceed with h is equal to 1 by 9. It is still dual feasible, it has not become negative. One of them has become 0, we will talk about it, but it has still not become negative. So, h is equal to 1 by 6 is acceptable as far as we are concerned. So, we could either pivot on h equal to 1 by 9 or we could use h equal to 1 by 6 and generate an all integer dual cut. The cut becomes different when you use h is equal to 1 by 9 and the cut becomes different when you use h equal to 1 by 6, because when you used 1 by 9 we had a minus 3 here, which gave us an objective function of 4 into 3 12, whereas when we use h equal to 1 by 6 we are getting a minus 4 here. So, this gives us 4 into 4 16. One can also understand this 12 and 16 in a slightly different way. For example, this is like your Cj minus Zj or Zj minus Cj. This ratio is your theta or minimum ratio. Because the pivot is minus 1, this will be straight away this product. 4 by 1 is 4, 4 into 4 16. We also know in linear programming that the increase or decrease in the objective function is the product of the minimum ratio and the corresponding Cj minus Zj or Zj minus Cj with the sign taken appropriately. So, this gives us a 16, the other one gives us a 12. Now, the question is, would we prefer to use 1 by 9 and create an all integer dual cut, which takes the objective function from 0 to 12 first, or would we use a 1 by 6 to take us to an objective function of 16. So, if we go back to very conventional simplex method, we had always used what is called the largest coefficient rule, but this is something like your largest increase rule, because from 0 we have now moved to 12 and we have moved to 16. So, it is advantageous now to look at h is equal to 1 by 6, so that we get into that 16 rather than we get into 12, because it is like using the largest increase rule in linear programming. So, compared to 1 by 9 we could now pivot on 1 by 6. But then we need to understand a couple of things. Now, at this point we have understood that 1 by 6 has a slight advantage, not saying great advantage, but a slight advantage, that it is able to give or reduce from 0 to 16. Remember, it is a minimization problem. So, it goes like this, at the end it will get adjusted. So, 16 is preferred to 12. Now, we have to answer another question. So, between 1 by 9 and 1 by 6 we would choose 1 by 6, but then every time we cannot be doing all these substitutions, like we have done 3 times, we have done 3 iterations, one with 1 by 3, one with 1 by 6, one with 1 by 9, and then we understood that 1 by 3 is not going to help lead us anywhere, whereas 1 by 9 and 1 by 6 are okay. We can't do this every iteration, trying to do it 3 times or 4 times depending on the number of negatives that we have. So, we need to have a formula or a computation through which we find the best value of h. So, a simpler computation would be that computation should also be able to do 2 things. If we take simply these are the negatives, and therefore, we could say 1 by 9, 1 by 6, 1 by 3, and suppose we take the smallest of them as a thumb rule, that would lead us to 1 by 9 with this. Whereas, we know that we have a way by which we could actually do this and get a 12, which is preferred to doing this to get a to do this to get a 16, which is preferable compared to pivoting on this and getting a 1 by 9 for h and getting up to 12. So, our computation should eventually lead us to that, and it should be able to say or give a h such that going beyond that h 1 by 6 in this example will give us infeasibility, which is what was shown by this 1 by 3. At the same time, that value should be a limiting value which can give us the so called maximum increase of this 16. We should be able to compute that kind of a number. Now, how do we get that? Now, we get that because the first thing we could do is, you realize here that this 0 came because of this 2. If you go back and how we computed this, this is our entering column, so the pivot column. So, we wrote this first. This is our pivot row, we wrote this 4, 2, 1 and 1, we wrote this, and then we said that this will become this minus this into the corresponding number here. So, 8 minus 4 into 2. As long as this element is 0 or 1 or 2, this will become non-negative. If this element were 3, then the corresponding thing will become 8 minus 4 into 3, which will become negative. So, we understand that as long as this number, which is 2, it was incidental that it is 2, is actually less than is an integer less than or equal to this divided by this. That is how that 2 comes. It is incidental that this 2 also came because of, when we used a 1 by 6 minus 9 by 6. I am not looking at that. I am trying to say that the binding ratio is actually 2, because this is anyway going to have a value of minus 1 here. So, we have to ensure that the kind of h that we use to get this should give us a value of a maximum value of 2, such that the resultant number that we get here is non-negative, and that number is the fraction or the lower integer value of this and this, which is 2. Therefore, we go back and define that when we generate a source, use this as a source row for the all integer dual cut, we now go back and see which are all the negative elements there. So, the negative elements are minus 9, minus 6 and minus 3. Then we see what are the objective function or what are the z values which are 8, 4 and 6. Now we will also realize that if you take these are negative values, let us assume these are positive integers, and these are negative values. Simply look at these numbers, take the smallest of this which is 4, take the smallest of this which is 4 and use 1 by 6, that is take this number which happens to be minus 6 and use 1 by 6. Let us say we have that is one number that we can think of. Now we will go back and say that for this to be the highest and the best value and for it to retain the dual feasibility, then what should happen is that this ratio is 2. So, 2 by 9 is the fraction here. So, we compute a 2 by 9 and then say if 1 by 6 is smaller than 2 by 9, I will accept the 1 by 6. If this computed number is smaller, then I will use that h. And when I use that h, whatever is that h that comes here, when I divide it by itself, the pivot will always be minus 1. So, I will be assured of a pivot element of minus 1. But if I look at these numbers, the fact that the ratio is 2 and 2 by 9 for h is bigger than 1 by 6. So, 1 by 6 will give me a better value than 1 by 9. My other alternative is to use 1 by 9. I said 1 by 9 would work, correct, because 9 is bigger than 6. So, when I use h equal to 1 by 9, I am going to get a minus 1 here and a minus 1 here, because 9 is bigger than 6, and I can always enter this, so that dual feasibility is maintained. But how do I know that 1 by 6 can give me a better value than using 1 by 9 is by comparing this ratio and getting this 2 by 9, which again as I said is the number that is going to come here at the end of the cut. So, the number that is going to come here at the end of the cut, as long as it is 2 or something, I am okay, and that is the 2 we are talking about, which is the ratio. So, if 2 by 9 is bigger than 1 by 6, then 1 by 6 can provide a slightly better value of h, which can give us a slightly higher number here, which is 16. Therefore, what we do is we take all those negative numbers here, then write only the negatives we take, we do not take the positives. It is easy to show that if one of these numbers is actually positive, it is not going to affect the dual feasibility in any way, because if the number is positive, then the corresponding numbers here will become negative, and therefore, we actually end up adding. We end up adding to these positive numbers, we do not end up subtracting. We subtracted because these numbers are positive. If in the original case these numbers also became positive because these numbers are negative, you have to look at it very carefully. All the 3 numbers are negative, h is a positive fraction less than 1 greater than 0. Therefore, all the lower integer values are negatives, negative integers, and when we do the row operation, because these are negative integers, other than this element all of them become positive integers, and when you have positive integers here, you actually end up adding something to this. So, dual feasibility is not affected. So, dual feasibility is not affected when I have a number that is positive here and not negative. Therefore, we take only the negatives to do this, because those negatives are essentially at the end of the day going to give us positives, which we end up subtracting. If some of these numbers are positive, then these numbers will become positive, and then these numbers will become negative, and then it means we end up adding something to these. Adding a positive quantity to a positive quantity is only going to retain the dual feasibility. So, we are concerned only about those numbers which are negative here. So, we take only those numbers, in this case all three numbers are there, and then we realize that the effect of the impact of each of these is essentially the lower integer value of the ratio of that number to the smallest number. It is always possible to take the smallest number here and use 1 by that and do a pivot, dual feasibility will be maintained. But then if we want a slightly higher value or the best value, so the impact of that is actually the lower integer value of the ratios. Therefore, we take that number, take this, divide by the smallest value and take the lower integer to give us 2, 1, 1. And then you have this 9, 6 and 3, and then take the smallest of the 3 numbers. So, 1 by 6, 1 by 3, 2 by 9, we take the smallest of these and say that h is equal to 1 by 6 as the value that we will use to generate the cut, because any value greater than that will give us dual infeasibility in the next iteration. A value smaller than that is okay, but at the same time, since we are interested in as large a value in the next iteration, we will take the corresponding value of h as the smallest of the 3 values. If we had not used this thing, we would have ended up with 1 by 9 instead of 2 by 9, and then we would have taken the minimum of 1 by 9, 1 by 6, 1 by 3. We could have used h equal to 1 by 9. We would have proceeded to another cut and another table with value going from 0 to 12. It will still lead us to the optimum solution, except that it could, not saying it will, it could take more iterations than what this will take. The approach that we use by doing this is equivalent of the largest increase rule, and therefore, we increase from 0 to 16 instead of going from 0 to 12. So, any value, this is like the best value. So, any value less than this would also give us, but as I said, it is good to get this 1 by 6 and not pivot on 1 by 9, so that in principle or on an average we may get into situations where with fewer iterations we will be able to solve this. So, that is how we get this value to choose between 2 by 9, 1 by 6 and 1 by 3. One has to understand how we get this 2. As I said earlier, this 2 comes from the lower integer portion of this 8 by 4, and as I explained here, that 2 exactly costed to 0. Otherwise, it will get some other number, and therefore, the whole thing will be very different. So, we take the lower integer value of this and do it. So, we have to answer one more question. What happens, for example, in the next iteration when we do this? Now, this I will have some other value at the end of the iteration. Now, what happens if one of the values is 0, like in this? So, if one of the values is 0, we actually do not have any issue. We can simply take that particular value here and use 1 by that for h. Just to explain that, let me complete this table. Let me complete this table and then show how the next cut is generated. So, we have to do this. So, this is 0 minus 4 into 4 minus 16 minus 18 plus 12 is minus 6, minus 15 plus 8 minus 7, minus 20 plus 36 is 16. This is 8 minus 4 into 2 0, minus 4 plus 6 2, minus 2 plus 6 4, minus 9 plus 12 is 3. This is 6 minus 4 into 1 2, minus 6 plus 3 minus 3, minus 5 plus 3 minus 2, minus 3 plus 6 plus 3. So, this is the next table. Now, if we want to proceed from this table, we once again take the most negative one, which happens to be here. Of course, we minus 7 is the most negative of the numbers, but then when we do this, we are having only two negative numbers, which are minus 3 and minus 2. We leave this out because there is a positive number here, and because we leave this out, we also leave out this 0. So, we take only this 4 and 2. So, the lower integer values will become 1 and 2. So, you have 2 by 3, 1 by 2. So, h is equal to 1 by 2 we will use to generate the next cut. If for some reason this was minus 4 instead of plus 4, then we would have taken that minus 4 also here, but then if we take a 0 here, then the lower integer value becomes difficult to compute, because 4 divided by 0, 2 divided by 0. In such a case, what we do is we simply treat it notionally as 1 and then say 1 by 4, 4 by 3 and 2 by 2. So, 1 by 4 will be the value. It is also not very difficult to understand that we are actually not making a mistake. If you see carefully, when we did the very first iteration, once again let me go back and explain. When we did the very first iteration, the values are 9, 6 and 3. H could have been 1 by 9, 1 by 6 or 1 by 3, the smallest of them could be 1 by 9, but then we said we want to make it better, therefore, we took this ratio and made this 2 by 9. So, the ratio actually helped us in increasing this numerator from 1 to 2, so that we got a slightly better value as the minimum, otherwise 1 by 9 would have been the minimum. So, the dividing it and getting the lower integer value is only a very notional way of understanding the kind of an increase. So, when we have a 0 here, one could easily take this as 1 by 4, h is actually 1 by that number is enough, but we are trying to get a slightly bigger value of the minimum by doing this division and putting it into the numerator. So, when we have a 0 there, you could treat it as 1 for the sake of computation of h, and 1 by that number will automatically become h. Of course, in this example it is not applicable because we have a positive number here. We would take only these negatives. As I said, this will not come. For this particular example, h will be equal to 1 by 2 and we can proceed. I was looking at a case when we had a negative here as well as a 0 here, then 1 by something, 4 by something, 2 by something. So, this 1 by something will be smaller and therefore, it will give the corresponding value of h. So, this is how the basic idea of computing h and understanding and getting the right value of h is done in the all integer dual algorithm, with a guiding principle that we are trying to follow the largest increase rule by taking the appropriate value of h, which can give us the largest increase. At the same time, do several things: retain the integer characteristic of the table, have a pivot equal to -1, bring in a feasibility in the next iteration, retain the dual feasibility, and try to give as large an increase in the objective function. So, this is how the all integer dual algorithm essentially works. Now let us spend a few minutes on the all integer primal algorithm. So let us take the same example that we saw in the previous lecture to understand the all integer primal algorithm. So we set up the initial table less than or equal to constraint. So you will have two slack variables x3 and x4. So we start with x3 and x4 here, and the decision variables will become minus x1 minus x2. It is a primal algorithm, primal feasible, dual infeasible. So we get a minus 1 minus 1, so it will become 7, 7 minus 5 and 7 minus 12 and 15. Now we once again have to find out, first we find out the entering variable in a primal algorithm. So we would enter these are already negative, so the smallest is the one that will enter. If we use, this is like using Zj minus Cj for a maximization problem. So smallest Zj minus Cj will enter. If we use Cj minus Zj for a maximization problem, the largest Cj minus Zj will enter. In this case both are equal, so we could enter either this or this. Just to show some illustration, let me enter x2. In a normal simplex we had only one possible, because this is a negative, so you do not use this to compute the minimum ratio. So 7 by 15 will be the minimum ratio and we would proceed. The only problem is we would have fractions. Now since we want an all integer algorithm, once again by the same logic a pivot of plus 1 is extremely suitable for an all integer primal algorithm, just as a pivot of minus 1 is suitable for an all integer dual algorithm. So to get a pivot of plus 1, what we do now is we now identify this as the original pivot element. The easiest way to get a pivot of plus 1 is by simply divide it by 15 or use h is equal to 1 by 15 into the other one and get it. So once again by doing this, this is an integer, this is a positive integer, this will not be 0, this will definitely be a positive integer because it is a pivot element. So 1 by this is always a positive fraction between 0 and 1. The only case that can happen is this can itself be 1, where h will be equal to 1. In this case h is equal to 1 by 15 because this is 15. If this itself is 1, then h is equal to 1. You do not have to need a cut, you can simply do an iteration, and only when this value is not 1 but another positive integer, then h will still be 1 by that positive integer which is greater than 1. Therefore h will become a fraction between 0 and 1, strictly between 0 and 1. So in this case h is equal to 1 by 15. So use h is equal to 1 by 15 and into this pivot or source row to get 7 by 15 is 0 minus 1 plus 1. This is your slack variable S1. Now actually this is the entering variable, this is the leaving variable, this is your pivot. So once again when you have a plus 1 pivot, what will happen is this feasibility will be maintained because you are dividing by the pivot. This feasibility will be brought in because you are dividing by negative of the pivot. So minus 1 divided by minus 1 will give you plus 1, plus the all integer nature of this table is maintained. And in this algorithm we do not do so much by trying to get the maximum like the largest increase rule, because you are anyway using the largest coefficient rule. In the dual algorithm we started with first a leaving variable and then an entering variable. So, once the leaving variable is chosen in the dual algorithm, the entering variable is chosen in such a manner that it gives largest increase. In the primal algorithm, the very choice, first the entering variable will come in, and that entering variable is chosen based on the largest of the numbers, largest assuming Cj minus Zj. In this case these are negative numbers, so they represent Zj minus Cj, therefore we take the smallest of them. Therefore, here in this case both are equal, so just to illustrate I took this. So, this is chosen based on what is called the largest coefficient rule. Largest coefficient rule, once again if you treat them as Cj minus Zj and values as +1 and +1, because they are Zj minus Cj, they are negative numbers, so you take the smallest of them and bring them inside. So, already there is some kind of a local way to try and get a good variable, so that is already taken care of. So, you do not worry so much about trying to get that largest increase, because you are working on largest coefficient. So, all that is needed in this case is that the pivot element is a +1. That will definitely be ensured, because we take this number and divide it. As I said, this number cannot be 0 because it is a pivot here. So, this number cannot be negative, it has to be a strictly positive number, and if it is a strictly positive number, there are only two cases, it can be 1, it can be greater than 1. So, greater than 1 will give you h is equal to 1 by this number. If it is equal to 1, do not create a cut, simply do an iteration, then proceed. Very similar manner in the dual algorithm also, if it turns out that h is -1, h itself is -1, then you do not generate a cut, you simply do a dual simplex iteration and then proceed after that, because the integer character of the table is anyway going to be maintained even without the addition of a cut. Cut essentially implies you are adding one more constraint, which means you are adding one more basic variable. So, you do not want to do that if your h is 1 itself. So, that is another thing that we learned to do this. So, before we go to the mixed integer programming, which is the next thing that we will do, let us have a very quick recap of what we have done in the last 2 lectures. So, we started off by looking at 3 algorithms that essentially use the cutting plane idea, which means to an existing simplex table you add another constraint or a cut, solve a resultant LP such that at the end of it the LP solution is feasible, both primal and dual feasible, or it is feasible and satisfies the optimality condition and gives an integer corner point, then it is optimum to the integer programming problem. So, we saw 3 algorithms: the Gomori cutting plane algorithm, the all integer primal algorithm, and the all integer dual algorithm. Now, these 2 algorithms ensure that the integer nature of the table is maintained, whereas the Gomori cutting plane algorithm allows fractional numbers to come into the table. We also saw the underlying relationship amongst the 3 by saying that whether it is a Gomori cut or whether it is all integer dual cut or an all integer primal cut, we will have or satisfy this equation, which is called the fundamental cut, which will ensure that no integer point is eliminated by the addition of the cut. And we also saw that from an LP solution, if we directly take a source row which has a fractional value, and it should be having an integer value at the optimum, and we take a source row and then use that source row directly here and put h is equal to 1, we get the Gomori cut. The all integer primal and all integer dual cuts have h between 0 and 1, which are fractions, and exploit the condition that the lower integer value of h is 0. So, the lower integer value of h is 0, your primal cuts and dual cuts are centered around only this term and this term. Now, depending on the primal feasibility and the dual feasibility that is required for these algorithms, H values are suitably computed, primal and dual cuts are generated, and we can iterate till we get to the optimum. I have not explicitly shown the iterations till we get to the optimum. The reader can continue to work out, because the mechanics of doing the all integer primal and dual algorithms have already been described in earlier lectures. So, in the next lecture we will address mixed integer linear programming in detail.